Let's discuss the relation between continuity and connectedness. In this theorem, we have a continuous function f between metric spaces x and y, and we have a subset E of x that is a connected set. And the theorem says that the image of a connected set by a continuous function is connected itself. So f of E is connected. So how do we prove that? So what does it mean to be connected? So f of E would be disconnected if we can write it as a union of A and B that are two separated sets of Y. Okay, so what we are trying to say here is for the sake of contradiction, assume that f of E, let's write it properly, f of E is not connected. That is, when we write IE, that means that's Latin for that is. Okay, it est. Now, f of E is equal to the union of A and B that are separated sets. And remember, separated meant that the intersection of the closure of A with B and the closure of B with A is in both cases the empty set. So here we have a continuous function, and continuous functions go well with taking inverse images. Okay, we have used that a lot in the proofs, so we will use that again. So here, just to get an idea of what's going on, let's say this is our metric space Y. Okay, and we have our, here, this is our f of E. Okay, it's separated in two pieces. And these two pieces are into, we can separate them clearly because we can take two sets, A and B, that are separated. Okay, we can see that the closures don't touch. Okay, and then we can look at the set E. Okay, here this would be our set E, and we can pull back from, this is our function f. Okay, that is taking E into two pieces, and we can look at the two pieces where that we had originally, that are the intersection of E with the inverse image of A, and let's call it H, which is E intersection with the inverse image of B. Okay, that splits in two pieces. Let's say this one, and then this one. Okay. And then when we apply our function f, the top part, G, goes to here, to inside A, the piece of f of E inside A, and the bottom part goes to B, okay? This is, of course, idealized, but it's just so that we get an idea of what's going on, okay? That's a way of saying the picture is completely wrong, but we get the right idea from it. All right, so when I write it like this, then E is the union of two pieces, G and H, and both of them are non-empty, okay, because of the way this is constructed. And here, what we want to show, let us show that G and H are separated. Okay, again, that means that the intersection of the closure of G with H is empty, and the intersection of G with the closure of H is also empty. Okay, we are able to do this, then there we have our contradiction, because this would mean that E is not connected, but by assumption it is. Okay, so that's the core of the proof, let's say. Okay, so how do we show that G and H are separated? Notice all the information we have it here on the right side. So somehow we need to use the continuity of f, the function f, to transfer information from G and H to A and B. Okay, we know lots of things about A and B, but we don't know much about H and G. So we need to use f to transfer that information. All right, so let's start. What I'm going to do, I'm going to show that the image of the closure of G is inside A, and the image of H is inside B, and that will be enough to show that the closure of G intersection H is empty. Okay, let me be more clear about that. Let's say it's enough to show that f of the closure of G is contained in A, and f of H is contained in B. Okay, because then G intersection with H must be empty. Okay. All right. So let's do this. First thing I want to note is that A is contained in the closure of A, and that means that the way we have defined G, okay, G is contained in the inverse of image of A, okay, and then by this property I just said, the inverse image of A is contained in the inverse image of the closure. Okay, so that means that f of G is contained in the closure of A. Okay, this is not yet what I want. What I want actually is f of the closure of G. Okay, but we will get there. Actually, it's quite easy, so let's cross this last idea and just make a remark, say, well, because f is continuous and the closure of A is closed, that means the preimage of the closure is closed. Okay, so we can actually improve on what we just did and say, well, because G is contained in the inverse image of F minus the inverse image of the closure of A, I can take closures on both sides, okay? But then because the right-hand side is closed, it won't get more closed because we take the closure again, okay? So here we get actually that the closure of G is contained in the inverse image of the closure of A, and then we get f of the closure contained in the closure of A. Okay, this is what we wanted. Did you see here? The first attempt didn't quite work, but we were not using the continuity for anything yet. But then when we use the continuity, then we get the little extra that we needed. Okay. Now notice that here we are all set because f of H is actually contained in B. Remember the way H is defined. okay, is part of the inverse image of B. Okay, so when we apply F, we get inside B. And this is all we need, because from these two together, what we get is that G, the closure of G intersection with H must be empty, because the intersection of the closure of A and B is empty. Okay, because A and B are separated. Notice you can see this by contradiction. Okay, if the intersection of the closure of G and H, if this was not empty, then this would not be possible. Okay, so we would be in a contradiction. And that's it. Now we can repeat the proof to show that G intersection with the closure of H is empty. Okay, we basically reverse the roles of G and H in the proof, and it follows the same steps. Okay, and that shows that G and H are separated, and E, which is the union of G and H, cannot be connected. Which is a contradiction. And that finishes the proof. Now, a very interesting consequence of this theorem is the intermediate value theorem from Calc 1. Okay, what does it say? It said that if we have a real function which is continuous in a closed interval, very important, that is continuous and it's closed, the interval, and we have that fa is less than c less than f of b, or the inequalities go the other way around, either way is good. Okay, but just for the sake of the statement, let's say f of a is the smallest, and this happens for some number c in R. Okay, when these two things happen, then there exists some number x in AB such that f of x equals c. This is easier to see with a picture. So let's say we have our real function that is continuous. Okay, so this is our function f, and this is my a, and this is b, and this is f of a, and this is f of b. Okay, and let's pick just some number c that is in between f of a and f of b. Okay, the fact that f is continuous means that the graph of f is going to cross the blue line at some point. Okay, so that is the value x in the open interval AB that is given by the theorem. Okay, maybe we could have a different graph. It could be something like this, or it could be something like this. Doesn't matter. You see that at some point, sooner or later, it has to cross the value c, because it's continuous. The only way to avoid this is a discontinuity. Okay, and this is very useful actually when when C is 0. Okay. To prove that there is a root, well, you don't say a root, a 0 of f of x equals 0 in AB. So let's do an example. We could have, for instance, the equation cosine of x equals the exponential of negative x. And we could be interested in showing there is a positive solution, a positive solution to this equation. And this equation, there is no algebraic way to solve this solution, okay? You can guess one solution just right away by trial and error. You will try easy values like x equals 0, 1, -1, things like that. If you try 0, you will see 0 is the solution. But that one is not positive. And other than that, there are no algebraic ways to find a solution. But you plug this in a computer, the computer will give you a solution. How does the computer find that solution? So the computer uses refined versions of the intermediate value theorem. Okay, and basically takes the function f of x, cosine of x minus the exponential of negative x. Okay, and we want to find x or some value such that this is equal to 0. Okay, so this is my value c in the theorem. Okay, and here the only thing we need to find AB. Okay, and this is again by trial and error. I leave for you to try. Okay, I'm going to try with A equal 1 and B equal 2. And it turns out that f of 1 cosine of 1 minus 1 over e, this turns out to be positive. And f of 2, which is cosine of 2 minus 1 over e squared. Okay, this is negative. Now, because one is positive and the other one is negative, that means that there exists x in 1, 2. We can call it x0 such that f of x0 equals 0. Okay? So that's the solution right there. And we know that there is a solution in 1, 2. But then we could apply the partition method that we saw already in the first chapter. Okay, and try again with 3/2. And maybe three things can happen. Either 3/2 is the solution, which would be very unlikely, or the solution is to the left or to the right of x0. That will mean that f of 3/2 is going to be either 0 or positive or negative. Okay, whatever the case, that will give us a smaller interval where we can apply the theorem. So we can apply the intermediate value theorem again in either 3/2 2 or 1 3/2. And we can keep iterating. We can apply this theorem a few times, maybe 3, 4, 5 times. And with that, we will be able to get a good approximation for x0, probably a couple decimal positions right. Okay, that's a way you can. And if you want 10 decimal positions, okay, maybe you can have a computer do this for you. But this is a way you can approximate the solution. Now, just to conclude, let me comment on how the the intermediate value theorem follows from the theorem on connectedness that we saw. This is very easy actually, because AB is connected because it's an interval. Okay. So because f is continuous, f of AB is connected. But a connected set in R is an interval. And that's it. Let's say if f of A is less than f of B, then we know what the interval is. Then the interval must be f of A to f of B. Okay, if f of B is the smaller one, then the interval would be f of B to f of A. But that's it. Once we know that the image of the closed interval AB is the closed interval itself, then for sure there exists a point, a point x in AB, such that f of x equals C. And that finishes the proof.